Okay, I'll switch between my iPad to laptop. No problem.
Ma'am,
Yeah.
maximum of our of students week 8 assignments are absent.
Oh, no, no.
We,
The answers were not corrected it. We will update it. We are doing manual correction, right? It's not like automatic correction as you did for week 7 until week 7. So it is taking some 2 days time. We are yet
okay,
to update it. So
okay, ma'am.
everybody will be absent for now. Once you update it, then you can see what the scores are.
Okay, ma'am.
Okay. So we've been saying lag versus speed compensator, but both using design of Bode plots. So I started with the lead. We will see lead again since we couldn't complete that, and then we will go to lag. If time permits, I will cover both lead and lag also. So in lead, what we were seeing, we saw how to um, establish a lead compensators, right? Or how to write a lead compensator. It would be S by 1 plus 1 by alpha t, where alpha should be in between 0 less than or equal to 1. Here, lag is in the other case, it would be S by 1 plus beta t, where beta should be greater than 1. So if you see here, I forgot to compare one more thing is last session. So if you plot your poles and zeros, you would see 0 here minus 1 by t, and somewhere here your minus 1 by alpha t. Why it is? Because the nature of how we choose the alpha value, because the alpha is in between 0 to 1, right? So if you choose something in between 0 to 1, for example, zero point 0.5, 1 by zero point 0.5, how it will be? Is it greater than 1 or greater than 0? How, like greater than 1, or how it will be? 1 by zero point 0.5. It's 1 by 1 by 2, right? Will be greater than 1. So it is more towards your left than your t. For example, if I choose 1 by 10 and if I choose 1 by zero point 0.1 as my alpha into 10, then this will be zero point 0.1, whereas this will be 1, right? So this is zero point 0.1. So this is always greater than this. Since it is in the negative direction, this will always lies to the left of the like a plane, S plane. Whereas if you see this, when I'm choosing beta equal to greater than 1, when I choose the numerator, that is 1 by t, let's take t is equal to 10, again same. But if I choose b is equal to some 2 into 10, then this will be 1 by 20, this is 1 by 10. Then this will always be towards the right than your 0. Is it clear, or any doubt in this?
Ma'am, therefore the value of alpha and beta depends.
Yeah, because of the values of alpha and beta, the position of your zeros and poles interchanged in your lead and lag compensator. That's what I'm trying to say. So
Uh,
always,
Ma'am, why we tell it as lead and why it is lag?
oh, okay. That is because how it improves your phase and gain margins in your Bode plot, or how it shifts your phase and gain margin in your Bode plots. For example, a lead compensator or a lag compensator's Bode will look something like this. For example, it has a slope of this, and this is minus 20 decibels per decade, and this starts at 0, and some negative it will come. The gain margin will be little negative. So I have in phase plot, uh, I am plotting in a wrong side. Wait, this is this confusion always happens, but it shouldn't be. So that is 0 degree. This is minus 45 degree, and this comes nearly to minus 180 degree. So your lag compensator will look something like this in phase, while it has a minus 20 decibels decay in your um, what do you say, magnitude. While if you see your lead compensator will look like this. It starts with 0, and it has a positive slope that is 20 decibels per decade, and it reaches some other maximum, some positive gain value that depends on your beta and t value, but in general I'm saying. So your phase will look something like this for your lead compensator. So this is 0, some positive degrees, maybe 180 degree or 45 degree, some positive degree as it goes above, and this goes down. This also changes, and this dip, where this dip ends and where this peak ends, it depends on your beta and t value, here alpha and t value. So if you see this lag compensator has the negative slope while lead compensator has the positive slope, where lag has the negative dip phase, lead has a negative positive up phase. So here if you see, this is improvising your phase, that's why we are calling this as lead. It is leading, it is increasing. Wherever you want to improve your bode or improve your phase margin, then you use this type of compensator. As it is improvising, increasing, we are calling it as lead. Whereas it is making a dip in your phase, or it reduces your phase margin, so it is called as lag compensator. So if you tune this and this together, we call it as lead lag. Always whatever you learn for lead and lag will apply together as a lead lag. Okay. So you don't need to study separately or explicitly for lead lag compensators. Just find the difference between lead and lag. Then you combine both for the third compensator. That is easy. But you used to get confused between these two. So study all the properties for one compensator, then you compare it against with the other one. If this has lead, first say lag has negative phase, then you compare it with, so if lag has negative phase, lead should have a positive kind of, you remember it. Okay. Any doubt in this?
No, ma'am.
Okay. So based on the value you are choosing here for your compensator, where it is, the position of your pole and zero varies. So in lag compensator, your pole lies to the right of your zero, where in lead compensator, your pole lies to the left of your zero. Clear? So pole will always be at left side. Here pole will always be at right side to your zero, not to any other thing. I'm comparing it with the zeros. Wherever, if you fix a zero at one point, leads pole will be here, lags pole will be here. That's how you should remember. Okay. This is one thing. And there may be some classification or match the following problems with this kind of properties. Choose, we will give the characteristics and ask you to choose which type of compensator it is. So it could be some potential question. Although we don't really ask you to find the compensator, these are like conceptual questions, right? This you can look for. Right. So how do we design a lead and lag compensator? There is a main question. So since we are not using it for exams, handwritten exams, I'm going to teach it with MATLAB little bit, but you also know how it is while solving by hand. So we are going to cover both. I'm starting with the lead compensator. So first of all, I will give you how this is in general it is. I will give you open loop transfer function, and I will give some specification like the KV should be this much, the space margin should be this much, and gain margin should be this much. This we call it as specifications. So what you will do is you will have a K with some transfer function. The first step, you will find a K value with the given KV value. That is the first step. Using this information, it's just like solving the riddles with whatever known we have first. So we will take with the simple example that we don't have any other options to it, right? We are just trying to, it's like solving Sudoku. Like, so we will start with the minimum dabbas, right? Similar to that, we are starting with the easiest one, that is KV. So with KV, your first goal is to find the K in your transfer function. Once you find the K, you will have a numeric transfer function like 5 by S into S plus 2 rather than K by S into S plus 2. Once you find this, First of all, you are supposed to find all the things that has been given in your specification so that you can see whether the question itself satisfies the specification or how much we have to make the deviations. If phase margin or gain margin have been asked in the question, you have to first find the phase and gain margin for this particular system you found. That is the second step. So I will have a phase margin and gain margin for this system. This is the one we have mentioned in the design assignment as specifications of a uncompensated systems. So whatever system you found after finding the KV has been called as uncompensated system. So when you design a compensator and make it together with the transfer function, it is called as compensated system as you compensate for the deviation. Clear? First, you should be clear with the norms. Don't do it blindly. Okay, if you don't have any doubt, I'll proceed with the next step. So once you find this phase margin and gain margin, make a comparison with the phase and gain margin that has been asked, that is desired, to your phase and gain margin of the actual uncompensated system. So you find the difference between these two and find how much you have to make changes. Some make some phi, some y value. So from this we are going to proceed. This I'm telling for the lead. Lag will have slight different change, but we are going to do the same thing. Okay. Fine. Once you find this, then you have to now the next step is to calculate the compensation. What to do to make this compensation works, or what to do to solve this deviation between the actual and the desired. For that, for your lead compensator, the first formula you can try is phi m, where phi is the to determine the amount of phase angle to be contributed by this lead network. That's what we are going to do using this formula. Where phi m we call it as maximum phase lead angle. This is what I typed in the MATLAB last week. I felt like it was not, you didn't understood it completely. So I'm writing it here. Phi m is equal to gamma d minus gamma plus epsilon. So we did it without using this formula. Actually, what we did is phi d is this desired phase margin. Like how much is your desired, that is how much you have to achieve. Instead of pm I'm using gamma d, that's it, there is a difference, both are same. For pm is a shorthand notation for phase margin, but actually it is mentioned using gamma d, that is desired phase margin, and gamma is your actual phase margin. So this is desired to be achieved, and this is actual in your uncompensated systems phase margin. So what do you want to find? The deviation. How to find? That is gamma d minus gamma. But instead of doing this, we are actually taking an epsilon, some minimum value. Usually we consider this as 5 to compensate for here and there, because we are doing all by hands, right? It's a trial and error method. So instead of doing actually as it is, we are just taking some here and there bound value. That is the 5. If you are, instead of considering like this, I am considering like this. That's it. Here and there 5 phase margin. So I'm considering some epsilon now. So the overall formula looks like phi m is equal to d gamma d minus gamma plus epsilon. This is your desired minus actual plus some like some values of epsilon, that is 5 in general. Then you find, now to find the compensator, what is your compensator? How it look like? It will look like 1 by s, s plus 1 by t, s plus 1 by alpha t. What are all the unknowns here? Somehow you have to find this alpha and t, right? So you should know the formula and the relation between your system and this alpha and t. So the next formula is to find the alpha. That is alpha is equal to 1 minus sine of phi m. What is phi m? This is the phi m, the deviation you found here, divided by 1 plus sine into phi m. So if you know your phi m, you will be able to calculate your alpha. So we have solved one riddle, that is alpha. The next riddle left is your t. So how can you find the t? Then again, the relation between t and this system and everything is, there is another term that is coming inside. So to analyze this to find this unknown t, that is the 1 by t into root alpha, where you know this alpha, you have to find this omega m and t. There is one intermediate step to find the t now. We know alpha. In order to find the t, we should cross this intermediate step, that is omega m. So for now, we don't know omega m. I'll tell you how to do from the figure. For now, assume that we know the omega m from the figure. I will tell how to find this omega m. Okay. So once you find the omega m, you have alpha already t. So t will be simply 1 by omega m into root alpha. You will find t also. So now you know that your controller s plus 1 by t divided by s plus 1 by alpha t. Everything you know. Now how to check if the compensator you designed is correct or not. You have a transfer function g. Let's call this is gc of s. You have a transfer function g of s. Do gc of s. So let's take, if this is my transfer function, I will simply multiply this with this divided by s plus 1 by alpha t. So this whole is called as compensated system, whereas this alone has been called as uncompensated system. This is called as compensator. So compensator into your uncompensated system is equal to compensated system. That's it. Very simple. So now you find again the Bode plot for this compensated system. Now you will find the phase margin and gain margin. It will be greater than your desired value. If it is that, then the designed compensator is correct. Otherwise, if this is also lagging from your original, you have to again design a different compensator. This is how it is a trial and error method. Clear? Any doubt in this lead compensator technique so far? No doubt?
No, ma'am.
Okay, fine. I assume that you understood this. I will move on with other. We will implement it then. Okay. Okay, I have projected my computer screen. So if you see this, hmm, okay. We'll do one problem as we did yesterday. I don't have that my PC here, so I'm starting from the beginning with some other example that I have in it. So my example says, okay, sorry, let me first solve this here and then come back here to the MATLAB.
Yes, ma'am. Please do in pen and paper. That is.
So the problem we are taking today is G of S is equal to K by S into S plus 1. That is lag. Sorry, for lead compensator we are doing first. And then I will explain lag and make one problem in lag compensator. So here, it's just the number difference between yesterday's and today's. The question expects the phase margin should be greater than or equal to 45 degree. Second specification is the gain crossover frequency. Instead of gain margin, this question particularly asks for the gain crossover frequency should be less than or equal to or less than 7.5 radians per seconds. And then gain crossover is actually omega gc. Okay. The third specification is the steady state error for unit ramp should be greater than less than or equal to 1 by 15. So here, this is actually an important point because sometimes in the question this can be asked for ESS, sometimes it can be asked for KV, KP, KD, KA. So if it is asked for ESS, first you have to find for if this is unit ramp. For example, if we use step, we will call it as 1 by sorry KP, right? If you use ramp, we call it as KV. If you use parabola, then it is Ka. For the same input, for ESS, this will be 1 by 1 plus Kp. This will be 1 by Kv. This will be 1 by Ka. And for Kp, we know limit s tends to 0, g of s. For Kv, limit s tends to 0, s into g of s. This is Ka, limit s tends to 0, s square into g of s. Just refreshing all the things. So if it is asked ESS, then you have to look for the input. Then you have to find that particular error constants. Then you have to convert it into E of S using this formula. Otherwise, if say straight away it has been asked as KV, you can start with this formula to find the K I'm saying. Okay. Don't confuse with, don't memorize the step, then you will be confused. See actually what it's been asked. Okay. I'm just writing it here. If it's E of S with input and error constant. If input is, okay, I will write it like this. Input, error constant, E of S. If input is step, error constant we call it as Kp, where Kp is equal to limit s tends to 0, g of s 1 by 1 plus Kp. If it is ramp, it will be called as Kv. That is the we use term as Kv. It's not called as G S into G of S 1 by Kv simply. If it is parabola, it will be K limit S tends to 0, S square into G 1 by K. Fine. So if it has been given straight away as KV, just find equate it to that formula limit S tends to 0, S into G of S equal to whatever value you have. Otherwise, do it in a reverse way. So now the given information, that is the ease of information out of all these things is E of S. So I'm proceeding with step 1, that is to find the K value. How do you find E of S for a unit ramp? So 1 by KV is equal to 1 by 15. So KV is equal to 15. KV equal to limit S tends to 0, S into G of S, where kv I know it is 15. So this will be limit s tends to 0, s into k by s into s plus 1. So this s will get cancelled. So k by 1, 15. So k will also be 15. Now I found k. So original uncompensated system is 15 divided by s into s plus 1. This is my g of s, right? Step 1 over. Next step is to find the phase margin, and since gain margin is not being asked, I'm going to find the gain crossover frequency according to the specification. So I have to find the gain crossover frequency from this Bode plot. So by if we are doing by hand, if it is being asked for exam, this you have to do the Bode what you studied in your week 7, I guess, finding Bode for a transfer function. And then you have to find the phase margin, gain, crossover frequency, gain margin, and all. Since we are doing design assignment only for this, I'm showing in MATLAB how you can do this. Now I know my transfer function. So I'm solving SHS. That is 15 divided by. So first I will say MATLAB how I'm going to use my SS. So S equal to TF of S. So whenever I use S, it will consider it as a transfer function S. It won't throw error. Okay. My system is 15 divided by S into S plus 1. Okay. This is my transfer function. It's not coming editor. Right. Okay. Maybe. Oh, this is the editor. So no comment problem. Okay, fine. Now I have a transfer function. So if I run this, so this is my transfer function, 15 divided by S square plus S. The next step is to find the Bode of the transfer function. So Bode of system. I'm running this so that I hope I will get it. Yeah. So I got it. If you right click on the Bode diagram and go to characteristics, all stability margin, you will see. So you don't, yes, here also the gain margin is infinity and phase margin is around 14.7 if you see here. There is no dot here, so it is infinity. So when you submit your Bode in your assignment, so next design assignment, now we use only root locus, no? So you have to do all this, all stability margins. You have to show me what is the gain margin and phase margin. I think I can do this with margin also. Let me try it once. Margin of system, what it is called. Yeah, you will get it here. So if you put margin of system like this here, you will get the phase and gain margin at the top of the figure. You can paste this image in your design assignment 2. So design assignment 2 will be based on the compensator design. Right. Now we found that phase and gain margin. So the next step is phase margin. What is the phase margin? That is 14 around, right? Um, what happens? Okay. Oh, okay. The all stability margin won't come here. Phase margin is 14.7. So my actual phase margin, that is gamma, I'm using R for gamma. Okay. Gamma is, since I couldn't do that in my keyboard, 14.7. I'm keeping it as 15 for now. It's actually 15, but what I need is it should be greater than 45 degree. So my gamma D is at least should be greater than or equal to 45 degree. Now I'm going to find the deviation between these two. What is the formula? Phi m, phi underscore m is equal to gamma D minus gamma plus some epsilon E. So this could be phi m is equal to 45 minus 15 plus some 5 degree deviation threshold I'm keeping. So this would give me 5, 20, 25. So my 5m here is 25.
Ma'am, 35.
35. I'm about to write 35. So, okay. Now I found my 5m. Then the next is to calculate my alpha value, right? With the invented phi m, the next step I can calculate alpha. What is the formula for alpha? As I showed in my iPad, it is 1 minus sine phi m divided by 1 plus sine phi m that we are going to calculate. So to calculate that alpha, I'm keeping alpha is a 1 minus sine of phi m, but MATLAB doesn't know what is phi m. So phi underscore m is equal to 35 here, right? So 1 minus phi m divided by 1 plus phi of it. So this we calculated from the figure, if you remember. My alpha is 0.03. Oh, sorry, so not sine. I missed it. 2.4. It's not possible. 1 minus sine m. 1 minus phi m. 35, correct one. Divided by 1 is sine phi m. What is sine of phi m? Sine phi m is minus 0.42. 1 plus 0.42 divided by 1 minus 0.42. It should be in between 0 to 1. No?
Ma'am, 1 minus 0.42 by 1 plus 0.4.
No, the phi m itself is minus. No, that's why.
Okay, okay. Yes, yes, yes.
Where I'm making mistake. Oh, that's also right. Sine phi m, where phi m is 30. If I put 30, 37, so that's 35. 1 minus 1 plus 0.64 divided by minus 0.64 plus. No, something I'm missing. So formula is 1 minus sine phi m divided by 1 plus sine phi m. Okay, okay. MATLAB is taking in radians. I'm sorry. This to be radius to degree. Merely substituting it will take it as radians, no? So it will be radian to degree. I think this is the one. 35. Correct. Okay. Then it should be sine of this. Radians to degree. Fine. We should get it. Hmm. It is 0.08 now. Radians to degree. Degree to radians. Okay. It is degree to radians because MATLAB will calculate in radians. So we are converting our degrees. Actually, this is 35 degrees, right? So our degrees to uh, radians for MATLAB convenience. So I'm using degree to radian. Since I have degree, I want to convert it to radians to calculate it in MATLAB. So degree to radian of 35 and as per the formula. Then you will get your alpha around zero point 0.2, which is inside the 0, 1. So this is how you also should be cautious, because alpha will never cross 1, should never cross 1 for lead compensator. So if your alpha is crossing 1, then you should be alarmed why it is happening. So there should be some issue. You have to check your things. Fine. Our alpha here is 0.27 that we found. The next thing is to find your omega n. In the notebook I have explained, right? So your omega, the relation to find the t. So for to find the t, there is an intermediate step, that is omega n. I am saving omega m as Wm, omega m equal to, the formula is 1 by t into square root of alpha, sqrt of alpha I'm putting here. So this is your t. So if you want to find your t, you should find your omega m. How to find the omega m? That is the question now. So your omega m, this is little crucial step. I'm thinking how can I explain it without confusing. Oh, your omega m is equal to minus 20 log of 1 divided by sqrt of alpha. So this is a formula for your omega m, but actually it's not, like we have to find the corresponding frequency at this value. That's how it is. So this is not actually omega m. I can call this as gain at omega m. Okay. Then we will call this as gain at omega m. So this will give you a gain value that is in decibels. That's in your magnitude. So if you find this magnitude in the Bode plot, you have to find the corresponding frequency. So the next step is to find corresponding frequency of gain at omega m. That is your actual omega m. Then you can substitute here. So the to find the gain at omega m, the formula is minus 20 log of 1 by square root of alpha. Okay, let me first calculate this, see if you understand this. We know alpha. Till this step you understood, right? Any doubt in that? If you have any doubt, please stop me there. Now I'm going to find gain at omega m. Let me call it as g omega m. Okay, g omega m should be equal to minus 20 into log of what is the value? 1 divided by sqrt of my alpha. This is the formula. What is the gain value it is giving? Okay, I'm already in front. Your gain omega m here is it really taking it? Okay, sqrt of 35. Okay, here also I have to give you that. No, I'm using alpha straight away, right? So I don't have to give. Good log. We log them. Nine to 7. And divided by answer. Log of answer. Answer into minus 20. And starting. Equal to 57 integers. We'll find the same thing. Okay. Here also you have to find the degree to radian. It seems to be that then only it is giving correct answer. Okay. We are converting everything into radians, right? No. No.
Ma'am, alpha value is already in radian.
Already in radian, right? So why it is not giving that? That's the question. So, shouldn't be degree to radian. But it is supposed to give -6 or 7 around. I don't know where I'm making mistake. Okay, wait, let me check it. How to convert it to log? I think I'm making some mistake in converting it decibels. Log of x, it is right actually. Mumbai square root of SQRT is correct only, no? Mumbai square. It is A here. 0.27. Okay, for now we are considering G omega ms -13. It is supposed to be around -8 or 7. Mm, There might be mistake in the textbook.
The result is minus 5.66. This is
First,
minus 20 star log 1 by.
you put it in calculator.
Yes, yes.
So MATLAB is making some issue here, right? They put log into no. Then why? Okay, let me convert it into steps and see. Then we should know how we should do in MATLAB, right? It is yes, 1.9. I'm again doing 2. Maybe log is being calculated in different base in MATLAB. Log of is log of is it's not there. Okay. Uh, okay, in MATLAB, log of something represents ln actually. So how can we calculate log then? Anything like log 10.
Ma'am, in MATLAB, log
Ah,
is using an E base.
log 10, I think it is. Let me try with that. Ah, okay. It is log 10, not log. Okay, in MATLAB, it is log. Using log is equal to ln. The keyword log is actually giving ln values, ln of x.
Yes, ma'am.
That's why we're not getting proper result. So we have to always find log 10 of x. Then it is log of x. Okay, good thing. I also don't know this. Log of, it's actually log of x. Right. Now we found the gain at omega m here. That is the minus 0.5, 5.6 around. Okay. Now we will see the next step is to find the frequency at gain at omega m. That is equal to omega m. So where is minus gain? Gain minus 0.56 comes here somewhere here, right? Minus 0.5. You can see the dragger, right? Where I'm dragging my cursor in the body plot. So the frequency is around 0.31 here. Minus 0.56. The frequency is 5.31. Okay. Now I found frequency that is 5.31 radians per second. Actually, as we calculated everything in radians in MATLAB, so it is radians per second. Then once we find the omega, it is easy. T is equal to 1 divided by omega m into sqrt of alpha. That's it. So I can write T is equal to 1 divided by omega m. I'm going to write this. The frequency was around 5.3, right? Omega m is equal to 5.3. So I'm going to use omega m into sqrt of alpha. Now I think that's it. So your T is around 0.36. Now I found T, I'm just commenting it out. T is equal to 0.36, whereas my alpha is 0.27. Now my compensator that I'm going to call it as comp, which is equal to S plus 1 divided by T whole divided by S plus 1 divided by alpha into E, right? Should give proper braces. This one closes, this inside braces. This is fine, this is fine. Let me try it once. Oh, no. Should, okay, I have defined yes as something. Okay. Uh, Basically, oh, so this is my compensator design. That is S plus 2.7 divided by S plus 10.18. That is my compensated design to compensator. And so you have to, the next step is to verify that that is working or not. Now I am doing, this is my compensator. Now I want to find the compensated system, that is comp system is equal to my G, what is the system? That is G of S into my compensator. Let's see how it looks. So this is my compensated system. So the transfer function has been increased from S square to S cube. as my compensator has a yes term. So this is my overall compensated system. Now I am going to plot a Bode plot for this compensated system and see if just to compare, I'm plotting it in a different figure. So this is my figure 2, this is my figure 1. This is for uncompensated system, this is for compensated system. Let me do show characteristics, all stability margin. Gain margin is still infinity, phase margin is 51. So I will just type it here. Sorry, margin of compensated system. So here, this is a compensated system. That is, phase margin is 51. Phase margin here was 15. So here it is 51. That is greater than 45. The criteria has been satisfied. And your omega GC value has been given, right? What is omega GC? Sorry. Omega GC, gain crossover frequency. That is should be greater than 7.5. So it happens at phase margin. So here, if you see, your GC should be less than 7.5. Your frequency is 2.09 k. So it is obviously less than. We have surpassed all the criteria here. So everything is satisfied. So we are claiming that this compensator is a good design. Any doubt on this? Similarly, we do a lag compensator. Some 10 minutes. Anyway, you have to go. Okay. Let me take a minute here. Okay. So we will do lag compensated design.
Ma'am,
Yeah.
we have to do all this in design lab.
Yes. In design assignment, you have to do. It's how you do.
We have to do calculation in pen and paper, that is in our copy, or
You can do it in your notebook, and then update it in the answer sheet, whatever question has been asked.
Asked. Okay, ma'am. Okay.
Or ma'am, in the week 9 graded assignment also, we have to design in the MATLAB or solve the question in the rough rough copy.
Oh, both MATLAB has been asked in the question, no? Wherever it has been asked, attach the MATLAB plot and solve by hand. Attach the figures only and submit the code you used along with this, with that PDF.
Figure means this the if we type the Bode and this figure will come, then we have to take the screenshot or that code we have to paste it.
You have to take the screenshot and paste it in your PDF. Or
Oh,
first do your handwritten PDF, scan it, and make it as a PDF, okay? And then attach the figure with the names, like this figure is for question number 2, figure 1 kind of. Attach
okay,
it behind that your handwritten PDF. Make it as a single PDF.
okay, okay,
You can merge or split PDFs online, right? You can use that and to make this. Use a separate doc to attach all the figures corresponding to your questions and make it as a single PDF and submit along with your MATLAB code you use as a zip file. Okay,
excuse me ma'am.
then yeah.
Yeah, one request.
Uh-huh.
Because of the quiz on 12th, we haven't gone through the week 9 content, and today
Mhm.
is the deadline. It can be extended for a few days to go went through the lectures, then understand what we have to do.
Actually, last time itself, we have asked too many persons in the team to extend the deadline. As you were nearing your quiz, we have given that
Yeah,
option.
yeah, ma'am. But for the
Um,
quiz preparation, other two subjects we have, so I was doing that, and I have done a small. I have left with the questions and some AES and DSD, so I have to do that also. So it is possible to, as we are not very much familiar with this MATLAB and this design, so it is very much. Difficult to understand what is the process and how this, suppose you have also done that log 10 and this we have to understand what the MATLAB is using and what we have to figure it out. That is why I am asking.
yeah, I understood. Let me check with the team. If it is possible, I'll try to extend it from my side.
Okay, okay, got it.
I'll
And
update.
but today is the last date. It can be possible that we get the info by the 7 or 8 p.m.
After this call, I'll check with the team, whoever is point of contact for me, and update in the discourse.
Okay, okay.
Is it
Thank
possible? Or not? Okay, sure. Fine. We will just cruise through the lab compensator because we don't have much other session left. So I want to cover it. So if you have some other session, you can leave for it and see the recorded session. So each lab compensator, same thing. The ultimate aim is same, but we have few different steps to find the parameters, that is beta and t here. So similarly to the lead compensator, we will do the initial step same. That first you have to find the k. Since I already explained this, this will also have some criteria like KV, phase margin, gain margin, or some gain crossover frequency, phase crossover frequency, whatever it has been asked. Phase crossover frequency. Okay, whatever it has been asked. Let's just take the weakest problem first and solve for it. That is, we have to find the k with respect to the kv or ka or kp that has been given. Otherwise, ess for some particular input they will give. Based on that, the first step is to find the k value. Once you find the k value, you are writing a uncompensated system as some k numerical value, right? Some transfer function s into s plus e or something. Whole uncompensated system you have. Until here, both are same. So then you are going to find the phase margin, general characteristics, that is phase margin, gain margin for the uncompensated system. and you are going to compare the phase margin of desired phase margin and against the actual phase margin. Similarly, designed gain margin and actual gain margin. So if the gain margin is asked in the specification, do this step. Otherwise, you can leave the step one, or you can compare only the phase margin, whatever it is asked. If it is asked gain crossover frequency as the last step, we don't really explicitly do that. We will do for phase margin and check if the gain crossover frequency also satisfies. Otherwise, we have to further increase the phase margin so that it satisfies that. That's it. We don't have any straightaway method to solve that. Then the step 4 is the same. That is your gamma n is equal to gamma d plus epsilon. Otherwise, gamma d, this is how we studied it, right? So this is just a rewritten version of this. Gamma n this side, rest of the things that side. That is your desired gamma plus some, here are the epsilon, that is 5 degrees that you will find. And gamma n is the phase margin of compensator system, or phase margin to achieve, I can say. So this will be taken from the question. This is given in the question. This we are adding together. So we will know what is the deviation we need to satisfy.
Excuse
Same.
me, ma'am.
Yeah.
Gamma n is equals to gamma d plus epsilon. How
Yeah.
we come to know that what amount should we add that epsilon can take
That is 5 degree. I used to tell, no?
every time?
Every time, yeah. It's just a bound we are keeping. It's like a ball. Instead of focusing on the point, we are focusing on the ball. That's it. We are keeping 5 here and there. It's
Okay,
just a, as we are
and
doing
this
trial and error, we are making this compensation.
okay, ma'am. And this 5D means
Gamma D is the desired phase margin that is being asked in the question. Here they will give a specification, no? That is
okay.
same. Whatever you do here, we are doing same thing here also. Just a different kind of representation as it is a different compensator. That's it. Same gamma D plus epsilon you are doing here, and differentiate, like subtracting your actual gamma, right? That's what we are also doing here. Just keeping it into a different variable. That's it. Okay, what else? The next step is to find the phase of new gain crossover frequency. This is the different step than your lead compensator. So we will be doing little more intermediate step to achieve the beta and t as we achieved here alpha and t. So we are going to find that beta and t here. How we are going to find is the intermediate steps. The intermediate next step is to find your omega GCN, that is your gain crossover frequency. In lead compensator, this is not mandatory, but in lag compensator, you are supposed to find it. Here we found the omega m, whereas the omega m called the gain at your gain crossover frequency. That's what omega m. Fine. Now we have to find the gain crossover frequency. The phase. This is gain crossover frequency. We are trying to find the phase at gain crossover frequency. That is the intermediate step. So if this is omega GCN, so the phase at omega GCN can be called as phi of GCN. So this is phase angle at gain crossover frequency. That's how we interpret this. So now this needs to be achieved, right? That is your gamma D plus epsilon, where gamma D is being asked in your desired phase margin. Epsilon is some compensation we add, just these two terms. If you want to compare it against your lag compensator, these two terms, yellowish terms. Just what it is desired, that's it. That is your gamma N. that we already found, gamma n here is 180 degree plus phi of GCN. So that's what we found here, phi of GCN, where phi of GCN can be rewritten from here to find the gamma n minus 180. So this is the relation between the phase angle and the desired phase margin, that is along with the epsilon. That's it. That's a, for example, if I ask you to design a compensator that has a phase margin at least 30 degree, then this should be 35 degree. That's it. 35 minus 180, that is your phase angle at gain crossover frequency. That is phi of GCN, phase angle at a gain crossover frequency, where phase angle is the below plot angle. For example, if this is my gain crossover frequency, the phase angle corresponding to this is the phi of GCA. That's it. That is a phase angle if you want to visualize the same. Then comes, we will solve problem. You don't worry if you didn't understand this step. Then the relation between this and that is that to find the parameter beta, the formula is 10 power AGCN divided by 20. That is the formula. Then you wonder what is AGCN, right? So your AGCN is the gain at the new gain crossover frequency. What is gain crossover frequency? This is, so A is gain at omega GCN, where phi GCN is phase at omega GCN. So all you have to find is the gain crossover frequency. That's it. So gain crossover frequency occurs when phase angle is minus 180 degree. That's it. Now, this is the relation. Once you find AGCN, omega GCN, you will find AGCN, then beta. Then the relation between T and other stuffs are T is equal to 10 divided by omega GCN. So once you find omega GCN, everything will be answered.
Excuse me,
Yeah.
ma'am. You told few seconds ago, gain crossover frequency is at minus 180 degree,
Mm.
or it is if the magnitude of g of j omega is equals to 1, that frequency should be gain crossover frequency.
Mm.
So I am confused with the phase and gain crossover frequency.
Okay. With the phase and gain crossover frequency. It is okay.
I think the phase crossover frequency is that which is equals to minus 180 degree. If the angle of g of j omega is 180 minus 180 degree.
I think you are right because I just mismatched that gain and phase crossover frequency.
Yeah, yeah.
Let me write it so that it will be easy for me to interpret. Omega GC. Okay, gain it will be. Okay, fine, correct. Correct. You are right. It's not visible, whatever I'm writing. Omega GC is equal to frequency at G transfer function, that is the gain of transfer function, magnitude of transfer function is equal to 1.
Are you writing, ma'am?
It's glitching.
Yeah,
I have written it. Can you see that it's glitching?
yeah, ma'am. Yeah.
Okay, let me close and open it. Okay, frequency at G equal to 1. Is it right? So then comes the phase crossover frequency will be phase magnitude will be equal to 1. Then this is when your phase is equal to 1, right? Frequency,
The
but
phase will
gamma
be
G equal
minus
to 1.
180 degree.
Clear?
Yeah.
Okay, fine. Now, if phase at gain crossover frequency will be different. So this will be different. Gain at gain crossover frequency will always be 1. That's how you found it. That was wrong, right?
Yes, ma'am.
Oh, fine. Good. Thanks. Now we will solve the same question. One question from lab compensator. So I am given with a open loop transfer function that is g of s divided by k into s plus 1 plus s into 1 plus 2s. That's what my question is. Okay. Now design a suitable compensator so that the phase margin is 40 degree and the steady state error for ramp input is less than or equal to zero point 0.2. So this is the question given. So if the steady state error should be less than or equal to zero point 0.2, let us take this as a upper bound, that is E of S is equal to 2 for finding the K. So if E of S is equal to zero point 0.2 for RAM, so if we use RAM, then we will interpret this as KV. E of S is equal to 1 by KV. KV equal to limit S tends to 0, S into G of S, that is K divided by S into 1 plus 2S. When I substitute S equal to 0, this will become K divided by 1, that is equal to KV. KV I don't know, so this can be 1 by SS. So KV equal to 1 by 0.2, that can be 5. Then K will also be KV, that is equal to 5. So my overall transfer function, uncompensated system, would be 5 divided by S into 1 plus 2S. So this is the final system for me. Now the step is to find the Bode and then in turn find the phase margin,
Ma'am,
gain margin. Yeah.
how do you write kb equal to 1 by 0.2? That is ESS given from
Ah,
ESS.
ESS equal to 1 by KV, right? ESS is given,
Okay.
so KV equal to 1 by ESS.
Okay.
So now the next step is to find the MATLAB phase margin and gain margin. I'm presenting my PC.
Excuse me, ma'am.
Yeah.
After finding the k value and
Ah,
uncompensated system,
ah.
so then we have to design a bode of that system, right?
Bode for this system. This is to find the, since you have K, you don't know what is K, right? So your
Yeah.
actual system only you have found now.
Okay.
So for this we have to plot Bode. So I'm doing lag here. My system. Okay. I'm doing same variable. When you write it again, you do a different variable. 5 divided by S into 1 plus 2 into S. That is my system. Is it clear? 5 divided by 2S square plus S. That's right. I'm just adding clear all, close all here. So close all the figures when I run this program to open a new figure. Now I have the system. Fine. Only this is from the lead compensator. That's okay. 5 divided by 2 into a square plus yes. It's right. So this is my system, new system now. Now I want to design a Bode plot for this Bode of system. To find it in a new figure, I'm putting figure. Let me do that's a separate section. Then I'll save it. Uh, and save it so that I can run the session. Now I'm running the section. So this is giving me Bode of my lag compensator system, whatever system we are designing right now. This also has infinity, and the phase margin seems to be 18 right now. Okay, let me do a margin section, run section. So your gain margin is infinity and phase margin is 18 degree, whereas you're supposed to design your phase margin around 40 degree. There can be a little bit here and there, that is fine, but it should be around 40 degree. This question is saying it should be 40, not less than or greater than. Now we want to shift the system from 18 to 40 somehow. And here, and the next requirement is what they have given. Oh, that is previous one. Same, right?
Excuse me.
Only two.
Yeah. The gain margin, phase margin is 18 now, and we have to get it 40, right? Exactly.
Yeah.
So how is this? How can we compensate it with the compensator?
Oh, it doesn't mean like lag compensator will reduce phase margin and leak compensator will increase phase margin always. In general, they will reduce. For example, when compared to lead compensator, lag compensator will reduce the phase margin. Not that completely it reduces. So for
Okay.
improvising, we can use both lead and lag. For example, in the previous example, the gain crossover frequency should be less than 7.5. That's what the second
Yeah.
requirement is, right? If you would have used the slack compensator there, the gain crossover frequency would have been greater than 7.5. So that second criteria won't be matched. So that's how you define to choose whether to choose lead and lag. Here it was not so clear. In some problems, it will be visible, like your gain margin will also be given. So during that time, you will be able to choose it easily. Otherwise, you have to do this trial and error method. That's why we are using MATLAB. We are not forcing you to do all it by hand.
But ma'am, trial and hit and trial method will take too much time.
Yeah, it will take too much time. But in MATLAB, it is comparatively very less, right?
Yeah. So,
You can
so
write code
first
to
of all,
find it.
one should have enough knowledge to deal the MATLAB.
You should know basic MATLAB codes, like how can you plot a Bode and how to write basic codes. Like if you know C, C++, Python, if you know the logic, then it is easy. But for converting Python, if you know Python, you can write the code in Python also. I don't mind. You can submit the Python code for me. But the plots and output should be visible. It's not like you are forced to use MATLAB. If you're not comfortable with that, submit the code in Python. That's fine.
Okay, ma'am.
But you should understand what you are doing, not like mere copy and paste from some LLMs and you don't know what you are doing itself. The code, if we read it, we will be able to understand it. It will be too complex if any LLMs have written it, and there will not be any proper steps. So if you do it by hand, there will be reasoning why you are doing the steps. Like you would have tried previously with some other phase margin, with some other gain value, but it would have not been used. Then you have again would have changed kind of. So I'm saying in that terms. Fine. Back to our problem. It should be 40 degree, and your there is no any other second requirements in this question, just a steady state error they have given that we already satisfy. Okay. Now we are trying to improvise it to 40 degrees from 18 degree, right? So right now the phase margin of the uncompensated system is 18 degrees. So in this question, they have given explicitly that you use lag compensator to do that. Most of the time, it will be given, even if you are asked to do by hand. I'm saying. Okay. Now we know what is the gain margin. The next step is to find the phase of the gain crossover frequency. First, you need to know what is a deviation, right? Now it is 40 and it is supposed to be gamma n, that is Rn I'm saying. Your desired is 40 plus 5, that is 50. You are supposed to make it to 50, not 40. I'm sorry. 40 plus 5. Okay. Your yn supposed to be, gamma n is supposed to be 45 instead of 40. And then comes your phase at your gain crossover frequency that you need to find. How do you find that? Your from your phase margin of the uncompensated system, that is gamma, which is 18 degrees. Phase margin of the uncompensated system equal to 180 plus phi of gamma GC, gain crossover frequency. This is the formula. What does phi GC then? Phase at gain crossover frequency. So first you need to know what is gain crossover frequency from here, right? So in your Bode plot, gain crossover frequency occurs when gain is equal to 1. So going to your magnitude equal to 1, when your magnitude equal to 1, your frequency is 1.45. So your omega GCN is equal to 1.45. Omega GC is equal to 1.45. That's clear, right? How we found? Gain crossover frequency occurs when magnitude equal to 1. So your magnitude, when I kept the cursor at 1, the frequency corresponding to that is 1.45. That is in radian per second. So it should be radian per second. To remember that, not in degrees, this is frequency. So it is radians per second. And then you are finding the phase at the gain crossover frequency. So when the frequency is 1.45, what is the phase angle? That you have to find. When your frequency is 1.45, your phase angle is minus 161. So that is your 5GC. Any doubt in this?
No, ma'am, not in this. But what is the y? Y is equals to 180
Sorry,
degree.
every time I'm confusing. That is gamma. Okay, since I couldn't write it here properly with the mathematical symbol, I'm using R instead of gamma. Where gamma is your actual phase margin. That is you found here, 18.
Okay.
I'm sorry for this inconvenience. Okay. So your gamma equal to 180 plus 5GC. You can find like this. Otherwise, if you subtract 180 minus gamma, that is your 18, you will have something like this. Or sorry, it would be 18 minus 180, right? You will have some 162. The same thing you are getting from the Bode plot. Both ways you can do. It will be same. By doing, when you're calculating by hand, you can use this formula. When you're using your MATLAB, you can find it like this. I'm showing both ways. Now you found your gain crossover frequency, and also your phase angle at gain crossover frequency, and you found your phase margin of the actual system. Now you're ready with everything, right? Then your gamma n, that is the desired plus some epsilon, that is 45, that you have to design a phase margin to achieve 45 degree from 18 degree. That's what we have left with right now. Now, you have to find a new gain crossover frequency. That is omega GCN instead of omega GC. That is actual gain crossover frequency from your Bode plot. The next step is to find the new gain crossover frequency. How do you find the new gain crossover frequency? By finding the phase at new gain crossover frequency, that is omega Cn, that is phi of Bcn. I know it is confusing, but just assimilate the steps for now and do it by yourself again. And if you encounter any doubt, please let me know. So now the relation between this phi GCN, that is equal to 180 degree plus gamma n minus 180 degree, where you know your gamma n, that is 45 degree. So phi GCN, new phase angle at new gain crossover frequency, where you want to shift your Bode plot for the compensated system. Happening in future, so you are calculating right now. So Rn, that is gamma n, is your 45, right? That it is here. Gamma n is desired plus epsilon, 45 minus 180 degree phase angle. That is your phi GCN, that is phase angle at your new gain crossover frequency. Okay, this is also a formula. We don't need it. It's minus 135 degree. That's your phase angle at your new gain crossover frequency. Now we are going to find what is the new gain crossover frequency. When finding the phase angle, that is minus 135, where it is happening. I'm dragging the cursor. The frequency is around 0.4 or 0.49, that is 0.5, let's take. So my new gain crossover frequency, that is omega GCN is equal to, where my compensated systems phase angle will come. I'm what do you call, pre-calculating those things. So with this, we are going to shift the phase angle from uncompensated to compensated system. Now we found the new gain crossover frequency. Now we are going to find this A. We are doing all these things to find this AGCN, to find the beta back. Now we have to find the gain at omega GCN to find AGCN. Gain at omega GCN, that is equal to, omega GCN is 0.5. So when I hover over 0.5, the gain was around 17. Magnitude is 17. So it is 17 actually, but in decibels it is. We have to convert it back from decibels to, we can keep it in decibels itself. So that is your AGC. Gain at your new gain crossover frequency. Yes. Now AGCN is equal to 17. The formula is, to find the beta is AGCN, which is equal to 20 log of, that is log 10 of beta. That is B for now I'm keeping. So now you can find the beta out of this, right? So your beta B is equal to, that is for your compensated transfer function, 10 power. If you keep log to the left hand side, if you bring log to the left hand side, it will be 10 power, not log, 10 power AGCN divided by 20. The 20 here will also come, right? This will be AGCN by 20. If I take log to the left hand side, it will be 10 power of. So this is your beta. Now we found beta. So what is beta value? 7.07 around. That is my beta value. Now I have T. I want to find T also, right? The formula for T, that this and all I have written in the notebook. You can go ahead and check with this. Omega GCN. This is your formula for T. So T is equal to 10 divided by omega GCN, that we already found, that is 0.5. This is your T. T is your 20. Now we have beta and T. We can just find the compensator system. Compensator lab, that is equal to S plus 1 by T whole divided by S plus 1 divided by beta into T. Fine. S plus 1 by t divided by S plus 1 by beta into t. That is your overall compensator, lag compensator, right? Okay. Yes, it's not. This is my lag compensator. S plus zero point zero 0.05 divided by S plus 2.85. Now the compensated system is equal to my system into compensated lag. So this is my compensated system. It comes around S power x cube or something. Oh yes. If I do a Bode plot for this, Bode of compensated system, I will get this margin of compensated system. Mm, it's around 1.7, 107. Actually, we did it. Some mistake here. It is. So it is supposed to be zero point 0.7, right? Sorry, 40, 45 degrees, right? But it is really huge. So we have made some calculation mistakes somehow. What is beta we got? Beta is zero point 0.7. Sorry, 7.07, it seems. IT is around 20. That is same. How come this has been increased dangerously? 5 into 1 plus 5 is that's system is 5 same. Instead of beta is 37 as in the textbook is making. Uh, I think I'm doing some mistake here. 1 plus S plus 1 by t divided by S plus 1 by beta t. Compensated lag systems. This one is the system, right? One section. Beta equal to 10. Until here, everything is same. Beta is actually it was given 7 as in the textbook, but we are getting 10. That's fine. But why it is shooting up like 1 point? Compensated system. Okay, I have missed one step. So this is not a compensated system. Actually, this is a compensated system. Uh, Actually, how we found the for this lag compensator is that we will do one more step that we do is 180 plus this No, in MATLAB, same only, no? Phase margin is 108, it's right only. While calculating by hand, we will do x plus 0.05, 0.05, okay, 0.02. Beta into t, 140. Because 7 into 10, it is 140. 1 divided by beta into t would be 2.8. And should be, oh, see, oh, I think that is a problem. Ah, good. So this is 16 point something. So there is a deviation for 16 point something. So if we put beta equal to 7, let's take, we will redefine this. 16.4. Okay. Just we have to redefine this formula a little bit. Look, whenever we are calculating this, we can take little, here we are taking 5, we can take some 7 or something to compensate for the deviation, and then we can work on it. Make a deviation between by increasing the epsilon or decreasing the epsilon. In general, we would take 5, but for this also, we would go until 10. If that doesn't make any change, then that is not the actual issue there. Okay, it's not getting changed for changing this. Oh, okay. Then here I have to change, right? If I add 10, that should be 3. I'm not using that variable as it is. Still same. But again, I think I'm not using this 5. Just rename it. Okay. If I change this I and I have to calculate according to that, right? For minus 150. I'm not doing everything by calculation here. You can hover around the frequency again and to check that. I think by changing the epsilon, we would be able to make it to that. There is no mistake here. Okay, that's it.
Up to what range epsilon can take the values?
5 to 10 maybe, like
But
3 to 10, 3 to 7.
so
Not
3 to
very
7,
big.
if we hit and by hit and trial method, if we put it the values and find all the things, then we get the phase margin which is required, that is 40 degree.
Yeah, that is possible. If you write proper code, it will be possible. Here I am writing like a formula only, no? If you write with if and else conditions like a proper flow of code, then it is possible to do it in a single run with
Okay,
possible epsilon values for loops and all.
okay, ma'am.
And in MATLAB, there are tools. If you go to Simulink, wait, view publish editor, there are options for Simulink. It is not showing you anything. In simulator itself, editor itself, it should show. If you go to Simulink, there are tools already available softwares that under if you install the Kalman filter, sorry, control systems toolbox, you will see some compensator design toolboxes for examples and examples you can see. See, there are many examples. You can use this also to do, but you should know how to do that. If you go into some, for example, if I'm going into this, there are videos explaining this, what the system does and how can you replace it, and how to tune your compensator to achieve your desired specifications. Everything will be given here. It's also available in MATLAB platforms. I think Python also have a like given the libraries for this. I'm not sure. I won't use Python for this thing, so I'm not sure. Okay, we are running out of time. I'm leaving. If you have any doubt, please post in discourse.
Only that request, deadline extension, that thing, week 9. Hello.
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 Somebody was about to ask something. I just
Yeah,
left.
yeah. The about the extension of that week 9, ma'am. Please consider
Okay.
it.
Yeah, yeah. I will speak with them and let you know.
Okay. Thank you,
Ma'am,
ma'am.
Yeah.
ma'am, these 8 and 9, these are included in NSIM also.
8 and 9. In some, I said like it's conceptual based question will be them. We won't ask you to design a lag compensator for this, that. Not like that. Just like I showed you, no? Maybe this kind of questions might come. We are not giving priority to that.
Okay, ma'am. Okay.
Wait, I will show you. This kind of questions might come to understand your, to check your understanding. So, what is lag compensator? What is lead compensator? How it defines? So, whether it increase your phase margin to the left or right, up or down kind of questions.
Okay, ma'am. Okay.
Okay. Okay,
Okay.
see.
Thank you.
Thank you.
Thank you, ma'am.
Thank you. Thank you. I will check with the team and let you about the
Okay.
extension.
Okay, ma'am. Thank you.
Thank you.